for tall people up here, so I'm going to have to bend over a little bit. Can everybody hear me okay? My voice tends to fade off a little bit. Good. Okay, we're going to talk a little bit today about, when we first started the session, we started talking about visible and invisible problems. That was the title that was posted outside. We kind of changed it because we thought that might be a little bit boring, because the visible stuff is obviously apparent. And so the idea today is to talk about some stuff that's not visibly apparent. So it's the stuff that you might have a tendency to walk past, you might not notice it. And so I'm going to show you some examples of stuff that I've had the opportunity of walking through and seeing in my career. So I think you've read the bios probably. I have the opportunity of looking at hundreds, and I've probably looked at thousands of buildings in my career doing physical due diligence. And so I get the opportunity to look at entire buildings right across the country from top to bottom and see lots of neat things. And a lot of the stuff that we see also gets investigated. So if we see issues where we think there might be a problem, we also get to do some investigations. And we also work in a company where we are doing investigations. So we see the sort of full gamut of stuff, which is really cool. What I want to do is start off with just a little backdrop, a little overview of some of the primary causes, like some of the big picture things that we see which cause deterioration. And then just go through a bunch of examples. And John asked me to get to some meat. He said you guys are really anxious to get some good content. So I want to move through a whole bunch of examples that I've seen that they thought might be useful to you. And so we'll just work our way through those. I've got a ton of examples. I'm going to move fairly quickly. It might be beneficial if you see something that really piques your interest, you want to ask a question, you might want to just ask it along the way. I'm fine with that. Just stick your hand up. And then we'll just try and finish it off with just a little bit of a wrap up and some preventive measures. And so I like to start off with this graph because this is a graph showing the total value of building permits across Canada. But what it's really showing is a trend in buildings. And you can see there were some building peaks, obviously, back in 1989, and then as recent as just before 2008 and peaking again in 2014. Like the value of building permits are being issued is huge. But what it's telling us is that the building stock is growing astronomically. Like the building stock is continuing to grow. We are not demolishing those big buildings that were built back in the 60s and 70s. They're continuing to be maintained. And so we're dealing with a building stock that is not only getting bigger and bigger and bigger, it's getting older and older and older. And for anybody that's involved with buildings, you know that the sort of typical, like a theoretical, if you will, lifespan for a lot of building components is around 25 years. And so if you go back to 1989, I'm not sure if you can see I think I lost my laser pointer, but the sort of 1989 cutoff, if you look at the area of the graph, the buildings that we've been doing major repairs on are all pre-1989. So in that sort of smaller part of the graph, there's a whole building stock that's starting to turn 25, and it's getting older. So there's a huge amount of work to be done coming down the pipe, and we have to keep an eye on that stuff. Not only the stuff that's turning 25, but that older stuff where we're starting to run into problems which we really haven't seen as part of the mainstay of the building repairs. Like there's your roofing, there's plumbing work, there's boilers, all that sort of regular stuff. But then there's another realm and another whole, sort of a whole group of things that are going to need to be done to these older buildings. So just keep that in the back of your mind as we go through the presentation. So obviously, there are things that are very apparent. And you walk past a building like such as this, it's very apparent. But there's lots of stuff that's just not so apparent. And you might walk past a building, or you might have a building that looks just like this, and it's very easy to walk past an issue that could be systemic, and it could be happening throughout the building and actually leading to some pretty major problems. A couple of the deterioration mechanisms that we're going to be really focusing on today are corrosion and freeze thaw. There's obviously there's a whole slew of stuff and mechanisms in which a building or building components can fail and deteriorate, but we're going to focus on the first two, corrosion and freeze thaw. So, one of the premises and one of the things that you just have to keep in the back of your mind, I think everybody knows this, is that steel rusts. I know it's not really terribly new to you, but it is a phenomenon that we have to deal with on a daily basis. And there's this whole chemical process that goes on, but basically you need iron, water, and oxygen to cause rust. I mean, that's going back to sort of high school chemistry, if you will. But in conjunction with just your normal rust, you can get very aggressive corrosion happening as well as soon as you introduce salt. And this is a great example this is taken from San Francisco on a pier that juts into the bay. And the extent of corrosion there is phenomenal. And the steel is rusting aggressively. It's caused the concrete to spall off. And I'm sure you're familiar with it to some degree. It's just a great photo that demonstrates that process. Another process that you might not be so familiar with is something called carbonation. And this is where carbon dioxide within our atmosphere can get into concrete and depacify the natural protective cover that concrete provides on steel and cause corrosion as well. Now that's a little bit more complicated. There's a lot of debate in the industry about how effective or how important this is and how relevant it is to the degree of corrosion. But our experience has obviously been that carbon dioxide is and does cause it does cause steel to become depacified in concrete. And so what that means is that the steel within concrete is naturally protected. And so I don't know if most people know that, but the inherent alkalinity of the concrete protects the steel. As soon as you turn the alkalinity to more of an acidic environment, which carbon dioxide does, it corrodes. It causes the embedded steel to corrode. That's a very important phenomenon that we need to be aware of. And one of the results of corrosion is obviously a loss of structural capacity. You're starting to lose section loss. But another interesting fact is that steel expands, and it increases in volume by about 10 times. And that expansive, that rust formation, as it's growing, it can impart loads on the structure that were totally not intended. The engineers are not designing for steel that's going to corrode. They're designing for the steel as if it's going to be maintained. So it can have all sorts of effects on the building structure. And then freeze-thaw action. In this environment, northern American environment, we have freezing temperatures, we have warm temperatures, and that constant freeze-thaw cycle leads to some fairly significant deterioration. And, we've all seen some brick spalling. There's some mortar joint deterioration there as well. And so it becomes very important to manage water on our building envelope. So that's I'm just trying to give you a little bit of a backdrop so that we can move into some examples now to show you some specifics on some buildings that I've had the opportunity of working on. So the first example here is a 1980s multi-res building, and no indications of water leakage on the interior. Nothing more than the staining that can be seen at the floor slab levels. And this is actually rust staining coming out from the floor slabs. And very easy to walk past this. And I guess subsequent to a review, it was recommended to do some further investigation and to do some openings in the walls. And so what you find after doing some openings is that the embedded steel shelf angles are in fact corroded, and they're corroded to the point where they are starting to lose structural capacity. And if I just go back to this photo, the design of this wall structure is such that these panels are supposed to be individually supported. So each brick panel is supposed to be supported by a shelf angle, and then the next panel down is supported by a shelf angle, and the next panel down is supported by a shelf angle. But as soon as you start to lose structural load-bearing capacity on those shelf angles, all of these bricks start to load up and stack. And so all of a sudden you get unintended loads coming down. So all the loads that are being taken by this bottom panel are all of a sudden significantly increased, because now it's starting to support loads from upper panels. And so it's very important to make sure that doesn't happen. If you start to get those stacking effects or loads being compounded within your wall assembly, you will have other issues such as cracking, spalling. You can have brick panels that start to bow and come loose. And so it's important to get that looked at. I just got a slightly better picture of the amount of corrosion that's happening within this wall assembly, and it is fairly significant. So,
what's the solution here for that building?
Well, the first thing to do is to check to see whether there's a stacking effect going on with the brick panels. And if that's the case, then you have to be very careful in relieving those loads. So you want to return the loads back to the shelf angles, and in order to do that, in some cases, you'll have to replace shelf angles. And in some cases, if the corrosion is not that bad, if there's still enough structural strength within the shelf angle, that can be cleaned. So it can be cleaned.
Ultimately, those walls are designed for water to get past the brick, so you want to provide a mechanism for that water to get out. At the bottom, you want to protect that shelf angle and allow the water to get out, instead of sitting on the steel shelf angle and corroding.
But if they're corroded past their structure.
You're going to have to replace them.
Capacity, you have to replace them?
Yeah.
And is the shelf angle then supporting the brick above it, is that correct? So each of the panels, so it's supporting that one story of brick. So how do you actually replace the shelf angle if the brick is actually resting on the shelf angle? Do you use pieces?
You do it in sections, yes, and you shore up the panel.
I'll add, it's an expensive process. We have one in Halifax that's underway, I guess, starting in a couple of years, and it's about $400,000 to do all the shelf angles for the whole building. So quite an expensive process.
You start at the top and you work your way down. You start relieving the load on the bottom panels.
Is that a common design practice to have various shelf angles at story intervals, or is it just because the shelf angles can only support a certain amount of weight from the bricks, so they break it up into those levels?
There are designs where the shelf angle is supporting more than one story of brick. The more common one that we see is the brick is actually supported on the floor slab edge. So it's sitting right on the extension of the floor slab. In these cases, it's the steel shelf angle.
Good. Okay, let's move on to a second example here. This is a 1960s multi-res building. Similar situation where there's no really apparent issues. You know, walking around the outside of the building, you really don't see a lot. There's one brick spall. There's no reports of leakage. And you know, when you start to take a closer look and you look at the upper floors in this is the same building, there's rust jacking going on. So as I said, when steel corrodes, it expands in volume and it can cause a jacking effect. So it's imparting a load, an expansive load. In this case, there's a shelf angle running along here, and it is corroded to the point where it is jacking up the walls above it. And so it's a similar situation where it needs to be, this hasn't been opened up and investigated as yet, but it definitely, there's something going on that's concealed there. It needs to be opened up, check the load, check the condition of the steel shelf angle, and then make a determination on what the repair is going to be, whether the shelf angle can be cleaned. In this case, I doubt it. It's probably going to need to be replaced. But also there's going to be some significant brick removal needed to access that shelf angle and to restore that wall back to a vertical plane. So this is another example of an elevation on the same building, and it's just a different wall area, but similar. Water is obviously getting into these shelf angles and causing them to corrode. So this is taken with a zoom lens, and from grade, this actually was more apparent than the other shot that I just showed. But keeping an eye out for this sort of vertical differential movement, you can see that there's a gap forming just above like where the shelf angle is. So that's an indication that we're getting some rust jacking going on at this building. And this is a shelf angle on the lower floors where I was able to measure some of the rust jacking going on. So you can see there's about a ½ an inch or about 12 millimeters of rust that's formed on the top surface of that shelf angle. And so with 12 millimeters, if you use a 1 to 10 factor, there's approximately 1 millimeter loss of section estimated on that shelf angle, right? So that 1 millimeter of the top surface of the steel of the shelf angle has expanded in volume to about 10 times. And you can see it. So that whole chunk of rust that's forming on top, that's the volume increase of about 1 millimeter of steel. It's pretty incredible. Like, it's really neat how it grows in size like that. All right, let's move into a garage example and a phenomenon called punching shear. So when we're looking at garages, we're paying particular attention to older garages and which have a construction where there are no column capitals and no drop panels installed. So you'll notice that the column in this situation comes straight up and meets into the slab. That's an older design. Typically, you won't see that type of design in newer construction. And we have bars, we have top steel, and then we have bottom steel and slab. And obviously we have some cars parking on it here. So what we're worried about, or what's of concern, is to making sure that the steel right at the column and the top surface is intact and in good shape, because that's providing a large amount of the structural load carrying capacity of the slab. And so what we're concerned about is getting a cracking phenomenon. If we start to lose capacity between that top steel and the concrete surrounding it, I've got another slide here. So if you start to get concrete delaminations in this area, you start to lose structural capacity very quickly. And this can lead to a phenomenon called punching shear, where the slab will not fail slowly, but it will fail abruptly and suddenly. And I think you've probably seen some of these cases where we have had some garage slab collapses, and this is a garage that was in Windsor that collapsed. I think it was this was in 2010, I believe. And so as you can see, there's obviously cars parked on this roof slab. What you will notice is that the columns remain vertical, and the slab has, if you will, what it's called punching shear, because the column effectively has sort of punched through the slab. And that's why it's known as punching shear. But this needs to be carefully evaluated. Older garages where there's potential for concrete delaminations, corrosion, especially on roof slabs or parking decks. Not roof slabs with landscaped areas, they're of much lower risk, in the case where they haven't increased the overburden over the years. But where you have the potential for corrosion right around the column to slab interface, it has to be checked on a regular basis. You have to understand the construction, and you have to understand the risk. And so
you get very little warning with punching shear. There's not a lot of evidence. The only evidence you do see is the cracking on the top surface. And unfortunately, in most cases, the top surface is covered with some sort of waterproofing or asphalt surface that the cars are parking on. So you will not see that cracking.
Would you see it from the underside though?
No, because most of the cracking is on the top side. If it's gotten to the underside, you're very far gone.
Okay, example number 4. I've got to get hustling here. So, anybody recognize the Algo Center Mall? Another corrosion issue. So, if anybody's read the commissioner's report, phenomenal amount of work went into investigating the cause of the collapse and all the investigation work that happened leading up to it. And it's amazing how many engineers were involved, how many contractors were involved, how many owners were involved, and so forth and so forth. But really, this is a case where there was obvious leakage. There were obvious problems on the inside of the building that were just ignored for years and years and years. And there wasn't an adequate amount of attention put on the concealed deterioration that was going on. They could address things like manage the water on the interior, not well, but they were able to capture it and direct it into buckets. All sorts of neat photos. But at the end of the day, it did lead to a collapse. And unfortunately, this beam that you see lying across the big opening here was the main culprit. And the connection where that beam interfaced with a column was the main source of the failure. And it was just corrosion. It was as simple as a parking roof deck, cars, bringing in road salt, leakage over a course of multiple years. There's debate and arguments over whether the design was inherently flawed, but regardless of that, there was ongoing concealed corrosion for decades, and it resulted in a massive failure. And so it's something that could have easily been prevented. And this is a shot from the bracket, or a similar. This is an adjacent bracket, I believe, between a beam to column interface, and they associated the amount of corrosion with similar to a marine environment. They said it was just phenomenal how much corrosion was there. So, really unfortunate circumstance. Okay, let's move on to something a little bit different. There's something called Kitec piping in the industry, which we're starting to see in newer construction. You're not going to see it in the 70s and 80s buildings, but because it was sold between about 1995 and 2007. And so PEX piping is a form of PEX piping, but it has an aluminum core. So if you look at the cross-section of the pipe, there's an aluminum core in the middle embedded between the PEX. And you can also identify it by the stamps on the fittings where it says Kitec. And the problem with Kitec is that there's a class action lawsuit out against Kitec because there's a problem with the fittings. There's the interaction between the aluminum between the PEX and the zinc, well, the fittings which contain a high content of zinc cause something called dezinkification. And that results in a product being formed within the pipe and expansive, another one of these expansive things, unintended consequence that forms, and it causes bursting of the pipe. And so you just can't predict that it's going to happen. It's not that old. It was only sold between 95 and 2007. There was a class action lawsuit that was settled, and there's a fund available for anybody that has Kitec and decides to change the piping within their building. So what we're seeing now is a slew of primarily condos that were built with this piping and going through a process of having to replace it. And they're replacing it mainly for insurance reasons, because once they get a leak, the insurance companies are saying, hey, we're not going to insure you because we know you have a problem. The industry knows it's a problem. You know you have a problem. And so we're going to force you to, we're not going to insure you, actually, if you maintain this piping. And so it's become a big issue. It's becoming a bigger and bigger issue in the marketplace. It's primarily focused on condos right now. But if you are looking at any new developments, or you have some new developments within your portfolio for multi-res, this is something that you want to definitely be aware of. So we'll go back into another wall example here, and this is an example of sheared header breaks. And a header break is, I'm going to have to blow through some of these here. A header break is where they're using the face brick, turning every 6 courses at 90 degrees to connect back in, to provide a lateral connection of the face brick with the backup concrete block wall. So this is what forms your wall structure. It's a combination of the face brick and the concrete block backup. And by turning the outside face brick and embedding it in the backup wall, which you can see in this photo here, you can see the red bricks, how they're tied into the concrete block. And on the outside, this is what you see. You just see a row of bricks which are turned on end. That's what forms the connection and basically combines to form a monolithic wall structure. No longer used. There are inherent problems with the design, but you still find it in older buildings, sort of 1970s vintage, but not typically later than that. So here's an example of a building on Eglinton where you'd look up, this is the north side of the elevation, you look up at this wall assembly and you really don't see much going on. But over the years you get shrinkage of the concrete frame, which imparts stresses on those headers, and it causes them to shear. And so as the frame of the building shrinks, and it's a very, very slow, small process that happens, you get differential movement between the face brick and the block. And because the bricks are not strong in shear, they just shear. So it looks like they look good. So looking at the bricks from the outside, you know what? They look fine. But there's no way of telling whether these header bricks are intact and remain so. And this is the building on Eglinton, which had, I guess it's 4 panels fall off. And this was earlier this year. This was about 2 or 3 months ago. It hit the news. So again, you need to be aware. It's definitely an invisible issue. It's something that, inherent to this type of construction. If you have it, it should be monitored and investigated. You have to do some openings to see if those header bricks are still intact. Today, in more modern construction, the lateral connection is provided with a little piece of metal, which is flexible, so it can absorb some vertical movement, and it still provides that lateral securement, which is critical. So, I'm not trying to show you really sort of the detriment or these extreme examples, but it just gets the point across. I hope I'm not coming across as showing all the bad stuff. But these are the risks, and again, just keep in mind the building stock that we have in Canada is getting older. We have a lot of these older buildings, a lot of these issues. As long as they're continuously reviewed, maintained, and understood, they can be managed. There are ways of managing this type of construction. So we're going to move in. Have I still got time to continue going through here, Martin? 5 minutes? Okay. Here's an example of some poor workmanship. So as you can tell, this is a newer building. And so newer construction. And looking at it, even looking up closely at the sealant work, you know what? It looks pretty good. You know, you look at it, it's intact, it's got a nice profile. But when you look at it a little bit closer and you start to stick your finger into it, you realize that it's not very well installed. And I've run across a number of buildings now where this is the case, and the sealant is just barely bonded onto the window frames by probably a millimeter or two. It's just very, very minimal. And so it's easy to walk past something like that. You're going to look at it, you'll walk around, look at the windows, new application, it's new installation, you think, wow, this is great. This looks really good. Stick your finger in it, and lo and behold, very little bond onto the substrate, and there's really very little material. I'm not even sure how they applied it with nothing behind. I don't know why there's a big gap behind the window frame as well. But obviously this is not right, and this is an example of just poor workmanship. So looking at a proper detail, there should be a minimum of 9 millimeters of bond. So we're looking at a sealant profile that's got maybe 2 millimeters, and the 9 millimeters is sort of the minimum. So it's really short. You're not going to see a typical service life out of that sealant. It's not going to last 15 to 20 years as it should. We've seen buildings where it's led to systemic sort of chronic leakage within 5 years. And so this is a common issue in the new construction. And just an example of some new sealant being applied and doing a pull test on it to check the bond, make sure that it's being installed properly, the profile is correct, there's enough material installed. So it's easy for a contractor to put a lot less material. It's going to save a lot of money, really, and time. So back to this fancy building here. Another example where easy to walk past. There were some indications of some water leakage on the interior, and in this case, I'll go through to what resulted. This has wallpaper on the outside walls, and as soon as you start to peel up the wallpaper, that's mold. Within the wall assembly, there's mold on the back face of the drywall here, and they are getting leakage. But it's been ongoing for a long time, and this isn't just in one unit. This is something it's throughout. It's a systemic issue. It's throughout the building. There's some systemic issues with the window construction and age, and also with the sleeves for those for the PTAC units. And then within the wall assemblies as well, there's corrosion. In this case, this is a steel stud backup. So the other wall we were talking about had a concrete block backup. A lot of buildings built sort of starting in the 80s, they built with steel stud backup and drywall interface, and then an airspace, and then the brick veneer. And so buildings in the 80s were known for this sort of new construction technique, and they were not well designed. The outer gypsum board was paper-faced. It's prone to getting wet. And as soon as gypsum board gets wet, it just starts to turn to mush. And it's also prone to mold. The steel studs, if they get wet, they tend to corrode out. They are a structural element to the wall. So as soon as they start to corrode, you lose that lateral support again. You're losing support for your bricks. You're losing that lateral support for the whole wall assembly. And so it turns into a much, much bigger issue very quickly. But this is all kind of concealed. It's tucked in the walls. When you have steel stud backup wall construction in your buildings, we always recommend doing some periodic testing to do some openings, check the conditions. Areas that are particularly problematic are around window corners. And as you can see in this first photo here, there are little foam gaskets that they use to make the joint between the horizontal sill and the vertical mullion of the window. And those fail after a while. So after 20 years of service, water that comes into the sill that's intended to drain out is getting caught in that corner, and it's going through the corners of the window frames, and it's going right into the wall assembly, like right in there.
Yeah, about 1 minute left.
Okay, I got to go. Okay. let's, you know what, let's just maybe, I'm almost done actually. This is a transformer in southwest Ontario where the door blew clean off the unit. I don't have a picture of it being blown off, but an inspection report revealed that it hadn't been inspected in a while. There's some heaters inside it which were disconnected. There's mouse nests in there. There's water in the unit. It's just a matter of it hasn't been inspected in a long time. But they're prone to issues, and so got to make sure that they're opened up, serviced, cleaned, inspected. It's part of just a regular routine maintenance thing. But that door blew right off the unit, shut down the entire building for a few days. So, okay. Now, preventive, a little bit of, on the preventive side, if I've got a minute or so, I would say one of the number one things is water management. Have a look around your buildings. Like, just take a walk around. And, I was at this property, and I love this photo because it just rained the night before, and you can see the difference of where there's a slight overhang on this side of the wall. There's no overhang here. There's no drip edge on this little cornice detail, and this wall is obviously getting really, really wet. And this is just detailing. And, if there was a proper drip flashing, something to get the water and kick it out away from the walls, these guys are going to save themselves a lot of headaches down the line. You just got to get the water off the walls. Like, you don't want water. The masonry is designed to get wet. It can absorb some water. It's designed to do that, but you want to kick as much water away from the walls as possible. It's going to save you a lot of time. And there's a great little study that was done by Building Science Labs. It talks about the effectiveness of drip edges, and even, believe it or not, there are actually different performance based on a different profiling of a drip edge. I mean, I'd be happy just to see any drip edge, but you can actually get better performance depending on how you design it. And so think about doing a walk around your properties, after a rainfall, during a rainfall, and see how is water hitting the walls, how is it getting kicked away, where is it going, what's going on. It's really powerful. Intrusive testing is going to be a must. It's just going to be part of our norm. And in this case, you can see, a concrete slab that sounds great, it looks great, the mastic is in great shape. As soon as you do a core, there's clearly a concrete delamination buried beneath the top surface that you won't be able to detect. You may not detect that with a chain drag survey or a hammer. In some cases, you just got to get in there. You got to do some openings, do some coring, and try and identify those concealed conditions. And it's a matter of understanding the construction, understanding the risks, and determining an appropriate review plan. So
good luck.
Thanks.
The RHB Insider Network is an RHB Inc. production, publishers of RHB Magazine, and the producers of RHB Newsreel.